Today we will start the next chapter, namely we will look at leader election algorithms. Now, leader election is a mechanism by which a set of processes decide that one of the processes is the leader, and the leader then performs some specific task. Okay. Now, leader election algorithms, like the other algorithms that we have studied in the past, they are used for specific types of distributed computation. For example, typically when you have a set of database transactions, for each transaction there is a coordinator. The coordinator is responsible for distributing the transaction elements into the different nodes of the network, and then collecting the result that happens of executing those transactions in those particular nodes, and then reporting the actual result back in one of the nodes. Okay. Now, there are cases when the coordinator of a transaction may fail, and then we have to elect a new coordinator for that. So, wherever there is a specific type of task which one process must execute or coordinate, we need a leader, and the leader election algorithms helps the distributed system to agree on who is the leader, and at the end of the algorithm all processes know that this process is the leader for this computation. Okay. So, when we look at leader election algorithms, we are going to look at different models. So, the first model is whether we are looking at synchronous algorithms or asynchronous algorithms. Synchronous means that all the processes synchronize at specific points of time, and based on that they decide they execute the protocol and elect the leader. Asynchronous means that there is no concept of synchronization. So, they all run asynchronously and then also elect the leader. We will look at anonymous and non-anonymous models. This is very important. Anonymous model means that processes do not have any unique ID, and the non-anonymous model means that every process has an unique ID. Okay. Every process has an unique ID. Now, we are going to come back to this issue, because this is a very important issue between anonymous and non-anonymous models. Then we look at uniform or non-uniform models. Uniform means that the processes do not have any knowledge of n, the number of processes, that is the number of processes is not known, or non-uniform where the processes know the number of nodes in the network. Okay. And then we will look at the impossibility result, which says that in the synchronous non-uniform model, leader election is not possible for anonymous rings. Okay. Now, you see synchronous means that, see, this is stronger than this one, right. Asynchronous means that there is no synchronization. So, if we even allow synchronization, if we allow non-uniform, that is everybody knows n, even then leader election for anonymous rings is not possible. Okay. And the reason why it is not possible is because of this anonymous. It is because there is no unique ID in the processes. So, we will show that no computation, distributed computation for anonymous models can give a leader. Okay. Now, before we come to that, let us first understand the difference between these anonymous and non-anonymous models. So, all these algorithms that we studied in the last few lectures, namely depth first, traversal, etc., were they for anonymous models or non-anonymous? In other words, did we assume that the nodes have unique IDs, or did we not? Where did we use that they have unique IDs? No, we just send vis to all our neighbors. Along each outgoing channel we send the vis. Right.
We identify that if this message comes from the node to which we have sent, which has been used or not used. Then how do we do that?
No, you know which channels are connected to you. Yeah, but you don't know who is on the other side of the channel, right? So when I send a message along a channel, a vis message or an ACK message, I just know there is some neighbor sitting on the other side, but I don't know the identity of that neighbor. Okay. So we never used the IDs of the nodes in those algorithms, right? So it was a anonymous model under which those algorithms worked. And before we go into election algorithms, let me show that if we assume that it was non-anonymous, in other words that every node has a unique ID and I know the identity of the neighbors, then the traversal becomes much easier. See, all this time that we spent in developing good traversal algorithms was because we did not know who is on the other side of the channel. We did not know the identity of the neighbors. So, suppose we knew the identity of the neighbors, then how would we do the depth first search? What would be the difference as compared to what we did? I mean, sending the vis, ACK and all that stuff. Suppose we knew every node knows who are its neighbors and knows their IDs. Then what? How can we improve on those algorithms?
First, we can put the ID of the node that has been traversed,
right?
And then not send it to that node because I know.
Now put that ID of the node where?
In the token.
Right, right. Very good. So that's what we will do. Okay, we will add to the token the list of visited nodes. Right. Now when a node gets a token, it knows who are its neighbors. It knows because we are looking at the non-anonymous model where everyone knows what are the, I mean, I know the IDs of my neighbors, right. Then I will see from that list which nodes are visited, right, and I will not send the token to them. So I don't need those vsac etc., right. So just let us go through the algorithm quickly. So I will come back to that. We will prove that result. Impossibility result will be proven. Okay, so let us see. Just like the previous algorithm, what we are doing here is we are setting father p as one variable. Initially it is undefined. Now the initiator starts by setting father p equal to p, just like the previous algorithm, and then chooses some q from the set of neighbors. Okay. And then it will do what? It will send the token, but now the token has a list. So let us call it T list, and it is going to put p because p is visited. Okay. This is the token now, the modified token, and this will be sent to q, right. This is the initiator. Now what is a non-initiator going to do? So, or non-initiator, or for that matter any process. Now for each process this is what it is going to do. What will it do? Firstly, it will check that if father is not defined. So, it will check if father P is undefined, then it will set father P P, right? Right. I am just checking whether everyone is awake. Right. Now, if there exists Q belonging to what, from where will we select the Q? Neighbors of P minus L, right? Then what are we going to do? Begin choose Q belonging to and then send the token to that neighbor, right? Now, what will be the token now? T list and L union P. P. P is this process. Okay. So, what is P for each process P? Now, else if there is no such neighbor, then what is it going to do? If P is initiator, what is P going to do? Yes, it will decide. Else it will send it back. Well, so, only thing is that then you do not have any other neighbors. So, you have to send it back to your parents. So, send T list Now, why are we again putting P here? Now, why wait, see, when a node, when P sent it to its children, it had already appended P to L, right. Then why does it again append P? Right. So, if P is a leaf node, then what will happen? It is going to get it from its parent, there will be no children. So, this is the only T list that it will send. So, it has to append this, right, and appending it multiple number of times is not a problem, because it is a set that we are talking about. So, it is not that it is going to increase the size of the token or anything, it is just going to check whether it is there, if not then it will append it. Okay. Union means no, it does not add another element, it just takes union. Clear? Anvesh, you do not look happy. You mean that the token, yes, the visited list will travel with the token. All right. So, that you have to bear with. Now, remember that when we talk about these distributed algorithms etc., we are not talking about traversing every node on the internet. Okay. We are talking about a computation which is working on a set of processes, right, and all these traversals etc., is working on that set of processes. It is the cone of influence of your computation, right, and hopefully you are not going to start a computation which needs to touch every node on the internet. That I mean, we are still not equipped to do that. Okay. So, that way it is okay. Well, now let us come back to election, leader election. So, in leader election, so therefore, you see that in our previous model for depth first traversal, we actually looked at previously the anonymous model, right. Now, we looked at the non anonymous model and saw that it is much easier to do it, because you know which are the neighbors. So, if the visited list is carried, then you do not need to send the token along the front edges, right. That can be easily avoided. But not having unique ID is not a good thing for leader election, right. Now, to show that this is impossible, we will prove the following theorem. What we are going to prove is that there exists no deterministic algorithm for election in okay, right. Now, to prove this, we will first assume that the ring is unidirectional. Okay. So, we will assume that the ring is unidirectional. What do I mean by unidirectional? What I mean is that in the ring, the channels are all either clockwise or anti-clockwise. So, I cannot send message in both directions on these channels. So, this is an unidirectional ring, and we will show, I mean it is very easy to see that if it is if this result holds for unidirectional rings, we can extend it without much difficulty to leader election in bidirectional rings. Okay. Now, let us say that these nodes are arranged as like this, that we have P 0, P 1 up to P n minus 1, and P I can send message only to P I plus 1, right. And we will define a configuration as follows, that C I denotes the state of P I, okay, that is C I, and we have M I to denote it denotes the collection of messages with destination pi. All right, and the global configuration is the concatenation of the Ci's and the Mi's, right. So, that is the global state of the system. So, I have the individual states of the processes and the MIs are the set of messages with destination pi, which may be in various places. Okay. So, a configuration will be called symmetric. So, let me write that. Now, what do I mean by this? See, let us first get this thing right. This is for process pi, right. This is configuration of pi. Now, see that because we are looking at an anonymous ring, right, there is that these processes, they do not have any ID, right. Now, each process is described by an algorithm, computation that it has to do is described by an algorithm. That is how we have studied all our distributed algorithms, right. So, we have seen that the algorithm for process pi is this, right. So, Ci denotes the state in that algorithm for the process pi, right. Now, when I say that a configuration is symmetric, then I mean that for all the processes, they are all in the same state and the same set of messages are in transit for all of them. Is that clear? So, what I mean is for all I and for all j, we have Ci is equal to Cj and Mi is equal to Mj. No, we are not talking about knowing on such. We are saying that a symmetric configuration is one in which all processes are in their same state of the algorithm and all the messages that are heading towards them are the same. See, in a distributed computation, every process executes the same code, right, all right. All of them execute the same code. Previously, in a non-anonymous model, we assume that each process knows its ID. So, you can distinguish process pi from process pj by virtue of their ID. Otherwise, they are executing the same code, they are only physically possibly located at different places, but they are executing the same code. If they are executing the same code, then they are going through the same states in their algorithm, right, and they are transmitting messages identically, all of them, So, I am saying, but they may not be executing all of them identically, they are sending the messages, but they are not synchronized. So, one may be running faster than the other, right. Okay. So, now if they are running faster than the other, then it is quite possible that when this process is in this state, this process is in some other state, because this one ran faster than this one, right. Then it is not a symmetric configuration. A symmetric configuration is one where all of them are in the same state, and the messages that are heading towards all of them are all the same. Are you getting? We are not talking about possibility at all. We are just defining that state is called a symmetric configuration. All right, that state is called a symmetric configuration. Okay. Now, a computation C is a sequence of configurations. So, all right. What we are going to show is that if the initial configuration is symmetric, then there exists a computation in which every configuration of the computation is symmetric. In other words, if all the processes they start in the same state, which is expected that they will all start in the same state at the beginning, and initially there are no messages in transit. So, for all I mi is empty, right. So, that state, the initial state, is a symmetric configuration, right, is a symmetric configuration, and in every other state, every transition, I mean we can have a computation where the system moves from symmetric configuration to symmetric configuration only, because if they are all synchronized, they are doing the same, running the same process, they are sending the same messages, then there is one computation in which every state is a symmetric configuration, right. Now, in that computation you can never elect a leader. Why? Because leader election means that one of the processes state will become leader and the state of the others will be non-leaders, right. But that cannot happen, you cannot have a difference of state between any two of them in that computation. So, therefore, it is not possible to have leader election in any distributed computation in anonymous rings.
So, same state means that just got message from the two different processes, but it does not have process ID because of that.
Same state means?
Same state of two processes means that
they are in the same, see every process is executing an algorithm, right. This process is executing this algorithm, Pj is executing this, but their code is the same code, right. Now, state of the process means what? In this algorithm where they are, what are the values of their data? Now, they are all the same in both Pi and Pj. If they are in the same state of the program, they have executed the same code starting with the same initial values of the variables, right. So, then everything is same for them, right. So, what we are doing is to state the whole thing intuitively, we are saying that look, if they are all identical processes executing with the identical initial state and in a synchronized way, then they can never disagree on something. They can never say that okay, one node is leader, others are not leader. How will that happen? If one declares it to be a leader, then everyone will declare it to be a leader, because they are all doing the same thing, right.
So in that case, even if it's a non-anonymous configuration, non-anonymous model and symmetric in all states, still there will be
no, what they will do is they will take certain decision based on their IDs. So the code will say that if my ID is this, then I will do that, right. You remember you have done fork in operating systems. What does fork do? Your process was executing, okay, executing lines of code, and then it encounters a fork, right. Again there are lines of code after this. When the fork executes, then exactly a copy of this process gets created, exact copy, same code, and whatever was the data values of the variables here, that is copied into the data values here. Now at this point of time, these two processes are exactly identical, but then that is useless, because they will keep on doing the same thing. So how do we distinguish between them? Process ID. That is why fork returns the process ID of the child to the parent, and therefore we can have, typically after the fork we will have, so you will save this, and then if PID is 0, then this is the child's code, else this is the parent's code. So you see, it is by virtue of this ID that we distinguish between the two processes, and they do two different things, right. So here also you see what we have just shown, though formally, intuitively the understanding is that if they are identical processes executing the same code with the same data, then they can never differ in any of the decisions. So how is it possible that one of them elects itself a leader, whereas the others agree that that is the leader? That can never happen, right. That is the problem with anonymous networks and leader election in anonymous networks. I am not making any assumption. I am saying that there is a computation in which they will only move along the symmetric configurations, and in that computation you will never be able to elect a leader. Is that clear? And from your algorithm point of view, you cannot avoid that particular computation. No, I am saying that that computation is always one of the possible computations. Now if you say that this is a leader election algorithm which works for anonymous rings, I will say how is it going to work in that particular computation.
But there can be other schemes without using ID maybe, which may end up in a leader selection algorithm.
No, I am just telling you that for every computation in anonymous rings, every distributed computation in anonymous rings, there is a possible computation in which every configuration is symmetric. Whatever computation you do, I am not talking about leader election, any computation that you do on a anonymous ring can go through only the symmetric configurations, and that discounts the possibility of having a leader election, because leader cannot be elected in a symmetric configuration, then it is not symmetric. right. That is the proof of this, and it is pretty intuitive proof. There is not much mathematics or anything behind it. It is pretty straightforward proof that they are all going to do the same thing. So, how come one will elect itself a leader? That can never happen, right. And because you are not adding any more dimensions into you are not putting any scheduling restrictions or anything. So, therefore, you can never say that that computation will not happen. If you could ensure that that symmetric computation will not happen, then to break that symmetry you have to do something which is asymmetric, and that you cannot do unless you bring some difference between the processes, and then they are not anonymous anymore, right. That is the argument. It only helped me in formalizing that, that these are the messages in this direction in transit and all that. It is not much of a help. You can easily extend the argument to bidirectional rings also. Now, let us move on to election algorithms in asynchronous rings. So, here we are talking about now henceforth for all algorithms, therefore, we are going to talk about this non-anonymous models, right. Because for anonymous models, even for rings it is impossible, and it is very easy to show that it is not, it is impossible for other types of networks also, right. So, but there can be probabilistic algorithms, right, but we will not discuss those right now. Now, election in asynchronous rings, there are we will start with this algorithm, which is Leland's and Chang Roberts algorithms. These two are algorithms which were discovered separately and are mostly the same. There is minor difference. If you look at Gerard Tell's book, both of these algorithms are given separately. You will say philosophically they are the same. It is only a little minor difference in the data structures and how it is handled. Okay. The idea that this one does is that every process which wants to contest the election sends its own ID to the node on left. Again, we are assuming that the ring is unidirectional. Okay. If an ID is received from the right, then forward the ID to the left node only if received ID is greater than own ID, otherwise ignore. Okay. And if own ID received, then you declare yourself as a leader. Okay. Now, there are a few things that should be mentioned here. In every election, the candidates must decide that they want to contest the election before the election starts. All right. So, it cannot be the case that after the election algorithm is executed for some time, then you decide that no, I want to contest the election also, right. So, that is not allowed. So, at the beginning of the algorithm, we assume that those nodes which want to contest the election, they will know that we want to contest the election. It is not, it does not have to be common knowledge, in the sense that every node does not have to know which nodes are contesting, okay. But those who are contesting, they must know that we are contesting, right. So, if I want to contest, I will know that I want to contest. I do not know whether he wants to contest, but I know that I want to contest, and he may not want to contest the election. So, he decides I am not going to contest the election, and he will remain like that throughout the execution of the algorithm. Okay, that is the assumption. So, what is happening here in this Chang Roberts and Leland's algorithm? So, every node which wants to contest the election So, let us put IDs with them, because okay, these are the IDs. Now, this is the direction. All right. Now, when, let us say at some point of time 6, 7 and 3 want to contest the elections, right. So, 7, let us say 6 starts by sending its ID to the left, right. Now, 7 starts sending its ID to the left, right. This one, when it gets 6's ID, it will simply forward it, right, because it is not contesting. When this one gets this ID, it will forward it, right. Okay. Now, when this ID reaches 3, okay, let us say that by that time 3's ID has travelled here. Now, when 3 gets this, what is it going to do? This one, okay, let me mark down this is 6, 6, 6, this is 3, 3. When this one gets the 6, what is it going to do? It will pass it, okay. So, another with 6 will go here, right. Now, when 7's comes to 6, what will 6 do? Pass it, right. When 3's go to 7, what will it do? Drop. So, 3's thing blocks here, right. When 6's one comes here, what will blocked, but what will happen to 7's one? It will go right through, right. And when the node gets back its own ID, it declares a leader, itself a leader. So, then after this whole thing has happened, okay, there are two ways in which, see, if they know the number of nodes in the network, no, but how will you know that there aren't any more coming, right. So, what is going to happen is, after the leader has elected itself, it will send a leader message to all the nodes, okay, and declare that it is a leader. Only the leader will know that it has been elected, right. So, it is like our old practice, remember the Ashwamedh Yajna, right. So, that used to take place where the emperor used to take out a horse, and then that horse will travel through all the kingdoms, and if somebody can stop the horse and beat the army which accompanies the horse, then the emperor cannot elect himself as the supreme emperor. But if the horse travels all of those kingdoms and then comes back unbeaten, then he starts the Yajna and he says that yes, I am the supreme leader, right. So, this is what exactly is happening here. So, the leader's token is going to go right round all of the nodes in the ring and come back to the leader, and then the leader knows that yes, there is no one who stopped this token, so I am the leader, right. This is for unidirectional rings. Okay. We are going to get into more types of structures in due course of time. Let us first finish with rings.
You want just any leader
The leader is?
Always all is maximum ideal number. It's unfair.
Who's contesting?
Yeah, but you don't know who is contesting. See, it's a subset of the nodes which is contesting. So, here it turned out that 7, which is the largest, is contesting, but it could have been that 7 was not contesting.
Yeah, I mean among the contestants.
Yeah, but you don't know who are the contestants. Unless there are no other contestants. Right. Now, these are IDs. Okay. Now, these IDs may not be static also. They can change. For example, you want the branch having the most balance to become the leader, right. So, they just keep the token carries the value of their balance, right, and then so you can do various kinds of things. I mean, it's just the algorithm that we are talking about, right.
Is that process synchronous? As in, if initially 7 is not taking part, but later it decides to take part.
No, actually, what happens is, you see, the need for leader election arises at a certain point of some distributed computation. Now, those processes which are active in that computation, they are the ones who are going to participate in the election typically. So, they all know that the previous leader is dead, or that we need to get a new leader, right. They all know, that's common knowledge, that's where the leader election starts. Now, if they do not know, which is in one algorithm we will see that case, then we must first wake up all the contestants and say that election has been announced. Okay. So, we will announce the election and then the election will start. Okay. So, that's a requirement that sometimes happen, and in some cases by virtue of some event they all know that now we have to get a new leader, right, and then they all start. But it cannot be, see, for example, in this particular case, suppose suppose 7 decides to contest the election after the 6's token has passed. Then we will have a problem, because 6 will get its token back and it will declare itself as a leader, and then 7, which initially had no problems with passing the token of 6, now says that no, I want to become the leader. Now, that you should not do. Okay. So, that's why we assume that when the leader election algorithm is in progress, every contestant knows that it is going to contest. But every contestant need not know the IDs of the other contestants, not even the number of contestants. So, they do not know anything about the other contestants, right. Now, what about the complexity of this algorithm? Worst case complexity is order of n square. Which is simple to see, right. It is upper bounded by n square is easy to see, because every token can in the worst case go around n times and you have n nodes. So, it is definitely upper bounded by n square. But what about the average case complexity? Now, average case complexity is more involved. Just let me give you the value of that. Actually, we will not go through the proof of this. I will just give you the result. Wait, just hold on. Now, is it obvious that the worst case occurs when all processes are initiators?
Because most of the messages will be blocked in that case.
Yeah, but can you show a computation where if fewer messages are fewer nodes are contesting the election, then we always have fewer number of messages than in the case where everybody is contesting, or is there a counter example to that? Now, what his argument is that if most of them are contesting the election, then many of them will drop out early, right? Depends on the direction of the ring, depends on the relative positions of the processes on the ring, all that is there. But the question is, given the positions of the processes and given the direction of the ring, is it the case that the worst case is always when everybody acts as the initiator, or can the worst case be in some other scenario where not everybody is contesting, right? First, try to get that clear in your mind, right? Then, assuming that all processes are initiators, this result says that this algorithm requires only order n log n message passings in the average case. The proof is there in Gerard Tell's book, right? Just browse through that proof, but it's quite non-trivial. So, I am just warning you in advance, but you should take a look at the proof and how you go about proving the average case complexity. You should take a look at that. All right. So, we will in the next class we are going to look at some more algorithms on rings, and then we will go into other kinds of networks.